Hey, so AP Physics C test, it's coming up. So let's just review. Yeah, I have nothing better to do because this thing is in a month. Oh well. Let's just start with a number line. All right. Oh yeah, by the way, this is going to be pretty introductory. We're just going to start with kinematics, and we're going to move our way through the units until we reviewed everything that's going to be covered on the Physics C test. So yeah, so first we're just going to cover some basics. Alright, position, acceleration, and velocity, and also some basic kinematic equations, and some harder ones. So let's say I have a number line, alright, and let's say here's the 0. I don't know. And 1, 2, 3, 4, here's the positives, here's the negatives, right? And let's say I have a particle right here. It's on the 0 on the number line. I don't want to draw it right on the 0 because that means I'll erase. Let's just pretend it's right on the 0, right? So we can say that its position is 0. So I would say position, which I will denote with an x, is equal to 0. Alright, so cool, we got position. Let's say it moves over here. Now its position is now 1, so it's changed to 1. Now, what if it took 1 second to move from here to here, right? In 1 second. Oh, and let's say the units for these are meters. When you're drawing graphs, you always want to label your axes, or else you might get taken points off, which is super sad. Alright, yeah, so this happens. Well, there's something called velocity now. Velocity is defined as our change in position over our change in time. So notice, I didn't say speed, because speed is always going to be positive. If I'm traveling this direction at 10 meters per second, I'm traveling at a speed of 10 meters per second. If I'm traveling the other direction at 10 meters per second, I'm still traveling at a speed of 10 meters per second. However, velocity is considered a vector, which means it has a direction. In fact, position is as well. But since we're only working on a number line, let's just ignore that for now and just say positive is going in this direction, negative is going in this direction, which is a lot easier to comprehend. Well, and it's mostly what will be used on the physics test anyways. So let's give an example of when velocity is positive. So in this example, we move from 0 to 1, so our change in x is 1 meter, right? We've changed 1 meter, and our change in time is 1 second. Usually we don't have to write change in time because our time is always going to be measured from 0. So usually it's going to be measured from like 0 seconds to however many seconds. We can always think of t as time elapsed, which is a good thing to keep in mind for now. And it's how I'm going to be formatting the rest of these videos. So 1 meter over 1 second, so that's just 1 meter per second, right? 1 times meters over seconds, 1 meters per second. Awesome. Now that would be our velocity, we just calculated it, but what if now instead the particle moves from here to here in a second? Well, the opposite thing happens here, right? So we go from 1 to 0. So our change in position is -1 because we've moved -1 spaces over. So our velocity would actually be negative. So now it's probably time to dissect what this means. Alright, so delta x means our final position minus our initial position, right? If you've calculated slope, you know, rise over run, we take the final rise, we subtract by the final rise over the or initial rise, and then we divide it by like the final run over the initial run. It's always final minus initial. And we can denote that using a small f and a small I at the bottom. Yeah, so this is our first equation. V is equal to delta x over t. Our next equation is A is equal to delta v over t. Acceleration is defined as something that is the change of velocity over time. And this acceleration can also be negative. So let's imagine instead of an object traveling from here to here, one thing to keep in mind is that our average velocity is our change in position over time, our total change in position over time. Like, if I travel from here to here in 1 second, right, that doesn't mean I'm traveling at a constant speed. I could be sprinting and then I slow down and then sprint again, and I'm still able to make it in 1 second. So my velocity could be fast, then slow, then fast again, but I could still have 1 second. But my average velocity is always going to be equal to this. Alright. Next, our change in velocity over over our elapsed time is going to be our acceleration. So if I go from 1 meters per second to 2 meters per second, right, in 1 second, that means my change in velocity is 1 meter per second, and my change in time is 1 second, so I end up with 1 meter per second squared. So these are the units for acceleration. Yeah, so notice again that I have delta v here. And delta v is just like delta x. It's equal to the final velocity minus the initial velocity. Awesome. So let's just write down all the things that we've learned so far. And while I'm doing that, you can imagine acceleration as, I'll give an example of how you can imagine acceleration. Let's say like we're on a car, right? And you're traveling at an initial speed of 10 miles per hour, but then you hit the gas pedal, and then you end up at a speed of 60 miles per hour. You've and you change that in a certain amount of time. That's your acceleration. You accelerated because you sped up. You changed your velocity in a certain amount of time. All right. So remember, acceleration is also a vector. We can go slower, and we would have deceleration or negative acceleration, like if you hit the brakes on a car. All right. So let's review what we've covered. X is position, and its units are meters, or m. V is velocity, and it is in meters per second, and a is equal to is acceleration, and it is in meters per second squared. Okay, so we have a few equations we covered. V is equal to delta x over t, which is equal to change xf over xi all over t. Similarly, A is equal to, V average. It's equal to delta V. Notice not delta V average, it's just delta V over elapsed time, which is equal to Vf minus Vi over t. I'm always going to think of t as elapsed time, remember. Yeah, so these are two basic equations that we've learned. These equations, average acceleration. Don't want to mix that up, right? These equations are always going to give the average, because let's say I started at a speed of 10 meters per second. Again, let's say I started at 10 meters per second and I go to 20 meters per second. I don't have to accelerate at a uniform rate. I can accelerate super fast. So let's say I go to like 19 meters per second in like 0.1 second, but then I spend like 0.9 more seconds accelerating just by 1 more meter per second. That, so let's say here and here, right? Let's say we want like vroom, vroom, like our speed changed from here. Oh, no, this is not good. All right, so let's say that we have on our graph, we start with a speed of 10 meters per second. We want to get to 20 meters per second in like here, let's say it's 10 seconds from here to here. Well, let's say I accelerated like this, whoosh. My average acceleration is still just going to be this change in velocity, delta V, over my time. No matter what, if I accelerate fast, accelerate slow, etc. Alright, so next equation, next, we're going to come up with these things called kinematic equations. These equations are always true, but what's not always true are these things called kinematic equations. So for kinematics, I'm going to write this up here, we're doing kinematics. Right? We are going to assume that acceleration is constant. Right? So that means this is never going to change with time. It's always going to be a certain acceleration throughout the entire time. So now we can come up with a few more. Equations. So probably the most famous equation is x is equal to 1/2 at squared. Delta x. Alright, so notice I never have to use delta a because a is always constant. There's not going to be any change in a. Alright, here is our equation. Our displacement, or our change in position, is going to be 1/2 acceleration times time squared. Awesome. So how can we apply this equation? Don't worry, at the end of this video we'll show how we can derive all of these, but it does require some calculus, so I'm leaving it more towards the end. So here we have this. How can we use it? Well, let's say that I'm standing on a building and I have a rock and I drop it. Well, we know at the Earth's surface, gravity, or small g, which is a type of acceleration. So g is a type of acceleration. Its units are also meters per second squared, so we know its acceleration is negative 10 meters per second squared. What does that negative mean? That means I'm going down. I'm going to say up is positive, down is negative. Just like in our number line, I said right is positive, left is negative. All right. Oh wait, sorry. It's experimentally determined to be not negative 10. Sorry, it's 9.801, 1 meters per second squared. But for simplicity's sake, we're just going to say it's 10 meters per second because it's a lot easier to do our calculations because I don't have a calculator. Right. So negative 10 meters per second. Ready? It's not, so I'm going to write this approximately equal to for now because it's not exactly equal, but we'll take it because it's close enough. All right. So let's say I dropped the rock and it took 2 seconds to get down to the bottom. How high was the building? Well, if we plug in our equation, we get delta x is equal to 1/2 times negative 10. We don't want to forget units. Meters over second squared times 2 seconds squared, right? So if we multiply it all out, we get negative 20. We get negative 20 meters second squared over second squared. So this just cancels out. These cancel out, and we just end up with a unit of meters, which makes sense because we're using this equation to calculate displace or our position change in position, which was in meters. What does that negative mean? Okay, well if you remember, delta x is equal. So I'm going to say delta x is equal to xf minus xi. Xf here the height is 0, right? So if this is 0 and this is negative 20, that means xi must be, we solve and we get xi is equal to 20 meters. That means our initial height, so the height of the building where we dropped it from, is 20 meters, even though our acceleration, even though we got a negative displacement. So that's how we use this equation. The second equation is something called the time not found equation. But before we talk about that, let's talk about how we can manipulate this to get two more equations. These two equations. It's actually relatively simple. We just multiply both sides by t and we get vt is equal to delta x. And we also get a t is equal to delta v. Alright, that's two more equations. Good to have in our tool belt. Yeah, that's good to have handy. And the last one is the time not found equation. Vf squared is equal to vi squared minus 2a delta x. What? Oh, sorry, plus. What does that mean? That's like, what? No, that's fine. It's kind of confusing, but basically it allows us to find a relationship between these velocity, acceleration, and distance without using time, without knowing how much time has passed. So how would we apply this? So let's say that we knew that a rock was moving at some initial speed or velocity, let's say 10 meters per second, and then it accelerated. Remember, this is a kinematic equation. Oh, sorry, these two are kinematic equations, right? So we assume acceleration is constant. Let's say it accelerated at some 5 meters per second squared, and it ended up with a final velocity, and so we ended up with some final velocity, let's say of like 20 meters per second squared. Okay? So now we don't know how much distance had passed from when it was at 0 meters per second to when it went to 20 meters per second. Some distance passed. We know it was moving because we had velocity, right? So we have change in position, but how much did it move? Well, we plug that into our equation. Final velocity is 20 meters per second squared. Oh shoot, no, 20 meters per second, because that's the unit for velocity we have right here, right? So we have 20 meters per second, right, squared on this side. On the other side, we have our initial velocity, which is 10 meters per second, and we square it, and then we're going to add 2a delta x. So we know 2 times a is 10 meters per second per second squared, and then we still have delta x, which is what we're trying to find, our displacement, our change in position. Well, we can just solve, and what do we get? We get 400 meters squared over second squared is equal to 100 meters squared over second squared plus 10 meters per second squared delta x. Alright, so now that we've arranged it like this, what we can finally say is we can say that we can rearrange and solve for delta x, and we get delta x is equal to this minus this, so 300 meters squared over seconds squared over 10 meters per second squared. This is not clear at all. Meters per second squared, right? So then 300 over 10 is equal to 30 meters. We have meters squared on the top, meters on the bottom, so we have meters left. Seconds over second squared, those cancel out. We get 30 meters. How much distance did it travel? It traveled 30 meters while it was accelerating. And that is how we would use this equation, right? It's not necessarily to calculate delta x though. If we have any three of the variables, we can calculate the fourth one. That's how these equations work. If we have all but one of the variables, we are able to calculate the other variable. So I will rewrite this equation so it's more clear if you want to look at it again. Alright, so these are all of the kinematic equations I'm going to talk about. For now. If you, so if you stick around, we're going to do the proofs of this one and the proof of this one. Alright, are you here to stay? So yeah, let's just go for that proof. Ready? Remember, this is physics C, so we're going to be using some calculus. Only for one of the proofs, don't worry. It's not that bad. So I'm going to assume that you know how to take a derivative for now. Alright, so acceleration is a constant, right? And acceleration is a function of time. Position is a function of time. Velocity is a function of time. They're all a function of time because as time changes, all the values are going to change. If we graph it, right? If we graph time here and we graph acceleration here, we said acceleration is constant over time. It's not dependent over time. So acceleration looks like this. Instead, what if we graphed our velocity, right? Our velocity would be constantly increasing over time because our acceleration is constant. So, it would be constantly changing over time. So if our acceleration was positive, velocity might look like this, where it's constantly increasing over time. At this point would be our VI, our initial velocity at time equals 0. Or wherever we define our start time to be. Alright, so velocity is constantly changing like this. What about position? Well, position is changing in a little trickier way. So let's analyze how position is changing. Alright, so AT, let's just say it's equal to some acceleration alpha. No, alpha is bad because it's used elsewhere. So let's say that we're going at some constant. Our acceleration is AC, or it's a constant. I don't know. Our velocity, right? We said our velocity is equal to A times T, right? Our velocity is AT. Well, our average A is going to be equal to AC because A doesn't change. Its average is always going to be itself. So V is equal to ACT. Ah, nice, ACT. Alright, that's cool. But there's actually a second way we can derive it. Okay, so we said that acceleration is change in velocity over time. So I'm going to say acceleration is dV over dt. Do you see where I'm going? Right, so what I'm going to do is acceleration is AC. Oh, sorry, this is VT. I will write this real quick. So we get AT is equal to d change in velocity over change in time. If I integrate both sides with respect to t, what do I get? Well, AT, I said, is just equal to some constant acceleration. So if I integrate a constant with respect to t, I simply get ACT. I'm going to ignore all the plus c's. I'm going to ignore all the plus c's for now. Actually, no, let's put in a plus c. Well, why not? Right? This is going to be a plus c for both integrations, right? We combine the plus c's into one plus c. Right? And then we integrate dv over dt by dt, so we just get vt. Vt is going to be our final velocity, actually. This c is our initial velocity. So if you remember from the previous equation, we had A is equal to, or A is equal to delta V t. which was equal, no, delta v over t, so sorry, at is equal to, so at, which is just a, right, because ac, because it's on average is the same, t is equal to delta v, which is equal to vf minus vi. Alright, interesting. So if I rearrange this equation, I get act is equal to vt minus c. C is our initial velocity, vt is our final velocity. That's kind of cool. Usually we actually I won't say any usually. All right, so that's one thing to keep in mind. The next thing to keep in mind is that xt is v is equal to dx over dt. So we integrate v over t with respect to t. What do we get? We have 1/2 act squared. We integrate this with respect to t, we get 1/2 act squared. And what do we get on the right side? We get xt. Of course, we have a plus c. And again, that c is going to be our initial position, because we said delta x is equal to 1/2 act squared. Alright, that's cool. So yeah, that's basically how we went from, so plus c, so I'm going to change the c, replace the c, plus x naught, or xi for initial, or sometimes you can write x naught for initial, it doesn't matter, right? Alright, so yeah, so we integrated like that. You'll notice something I didn't do is I purposely left this, remember there's a plus c here, but which was equal to vi, but I purposely didn't integrate that part. And the reason is because with our kinematic equations, we usually assume our initial velocity is 0. Like if we're dropping a rock, or if we're dropping a rock from the top of a building. But actually, there's a more complete form of that kinematic equation. And we can get that by integrating this function with respect to t. So what is that? Remember, xt is our final velocity. These are all our finals. Our finals. Alright. If I integrate this one, what do I get? Well, here I get 1/2 act squared. 1/2 act squared plus v initial t plus c, which I said already is our initial position. So our final position is going to be the sum of these. That is the more complete form of that kinematic equation, and we just found it using calculus. That's kind of cool. Next thing we're going to do is we're going to move this over on this side, so we get xf minus xi, or just delta x, is equal to 1/2 act squared plus vit. That is another way they might write it, except, they'll probably just say a, because a for acceleration. We know it's constant, so we can just say a instead of ac denoting it's constant, because we know it's a constant, yeah. Alright, so this is a cool equation. But now, let's move on to the other cool equation that we had. And this one requires no calculus to prove. It just requires a bit of fun algebra and the previous kinematic equation. Alright, so what was it? Vf squared is equal to vi squared plus 2a delta x. Well, that means vf squared minus vi squared is equal to 2a delta x. So I can change this into vf minus vi times vf plus vi is equal to 2a delta x. Alright, so if you remember, we said that the v average is equal to delta x over t. Alright, how would you calculate the average velocity? Well, remember, this is a kinematic equation, so our acceleration is always constant. If our acceleration is always constant, our velocity looks like this. What does that mean if our velocity looks like this? That means the midpoint of the velocity, right? So the average velocity is just going to be the middle between the final and the initial velocity. So I can say that this v bar, or v mean, is equal, instead I can write it as vf plus vi over 2 is equal to delta x over t. Alright, that's real cool. So we got this part down. Now we can rearrange and we can say vf plus vi is equal to delta x, or 2 delta x over t. Next thing we want to do is recall our other kinematic equation, which says that a bar is equal to delta v over t. What? Well, sorry. Okay, so yeah, delta v is equal to vf minus vi, and then we can multiply t on both sides and we get a t. I'm not going to put the average. A is constant, so we're just going to say it's a. Right? Well, what if we multiply these two things together? Well, then we get vf minus vi times vf plus vi. What happens when we multiply 2 delta x over t times at? Well, we get 2a delta x. Exactly what we set off to prove. We just proved that this times this is equal to 2a delta x. Boom. And that is the proof of that one. So I hope you enjoyed. Oh, one last thing. College Board is a papega. So they'll this year they'll probably make you draw graphs about, maybe it could possibly be about position, acceleration, and velocity. Well, let's write down our kinematic equations again. A f t is equal to a. We have vft is equal to at. We have xft plus vi. Xft is equal to 1/2 at squared plus vit plus xi. This is an equation of a horizontal line. Acceleration, when plotted against time, looks like this. So this is a vt. Velocity, when plotted against time, this is the equation for a line, mx plus b. So it might look like this. And then, position, this is an equation of a parabola, where t is our, like, x in that case, where we usually graphed it. So here's our position, here's time. And who knows how it might look like, but it might look something like that. And that it would be what they look like. This would be a general shape of what they look like. Position is a parabola, velocity is a line, and acceleration is a horizontal line. Yeah. So, yeah, I hope you enjoy your day, and thank you for watching to this point. I honestly am just rambling at this point, but I think that's kind of cool you're watching, and yeah, happy studying. Hope you do well on the test.